And then the other big event is erosion. And oftentimes we use these terms more or less interchangeably, but erosion more technically means the removal of material from one place to another. So that's the transport of rock material. So when the river comes and washes the sand down the side of the mountain, then that is erosion. That's movement from one place to another. And there are a variety of agents, wind, rain, all of these things. And there are other things too. For example, I mentioned solifluction, which is the slumping of soil down the slope of the mountain fairly slowly, and yet nevertheless you do have the movement from one area to another. So here you see an example of mechanical weathering, breaking up this material broken into smaller fragments. This can be exposed now to wind or rain, which will then wash it and move it from its location here somewhere else. I mentioned frost wedging last time, which is a common event. Water enters into a crack, and then it freezes, and the expansion of the ice shatters the rock, and so you have the breakup of the rock material. I'm pretty sure that's what happened here. I can't imagine anything else doing that or is likely to have caused that. Chemical weathering is acids acting on rock surfaces, and you see evidence of it in a lot of situations. Most commonly, though, in karst terrain. Karst is typical landscape where you have limestone that's been exposed to running water. And so the water in contact with the lime rock creates carbonic acid. And so that calcium carbonate will eat into the rock and create typical caverns, such as Mammoth Cave. Here you see limestone, and when that's dissolved, then it creates all kinds of unique rock characteristics that are recognized in these areas of lime accumulation. So this is all referred to as karst topography, and it's all related to limestone, sometimes more advanced, sometimes less advanced. I mentioned the case of the disappearing river in Florida, the Santa Fe River, that in through the area north of Alachua or Gainesville, the river runs into a hole in the ground, a big sinkhole, and then it just disappears, emerging many miles downstream to eventually flow into the Swanee River. And of course you get these typical formations in caves where the dissolved minerals in the water in these environments, they will accumulate, form stalagmites, stalactites, where they're dripping and bouncing off of other material, making very interesting, spectacular features. So most of the big caves, most of the famous caves in the world are formed in this fashion. So you look at Carlsbad, New Mexico, that's dry. There's not much water there today, but at one time there was. And so these areas were formed in that fashion. Sinkholes, we talked about that as being a consequence, again, underground cavities and caverns that ultimately collapse because the roof of the cave is no longer able to support the overburden up above. Also talked a little bit about erosion, running water, carrying material from one place to another. Talked about the cycle of erosion, various descriptions of streams. Here's an old age stream, this serpentine pattern across the landscape where the river changes course periodically, centrifugal force eating out underneath the outside of these banks and then filling in on the inside. And so the river gradually reshapes, redirects itself. And here's a case where it's breaking into the lower portion of the channel. And so we'll be left here eventually with a portion of the stream that's no longer connected to the main flow, and you have what's referred to as an oxbow lake. So if you're from Mississippi or Louisiana, you're very familiar with those kind of features on the landscape of these old age rivers. Wind erosion common, erosion along the coast also as well. And then we ended last time looking at the effects of glaciers, these striations on the surface are caused by movement of ice. Ice sheets during the period of continental glaciation would scour the surface, move material along, and so both weathering and erosion caused by large blocks of ice moving along and scraping the surface. I use the analogy of a bulldozer in a field, and that's essentially what these ice sheets do. They move back and forth across the surface as a bulldozer would in an open field, and you're left with deranged drainage patterns. So you've got puddling like this. The river systems that might have existed previous to this then get completely obliterated by the action of this ice. And so here are examples, areas in Canada which are Alaska exposed to glaciers, and you can see all of these essentially puddling, which these in this case would be lakes up in this environment. And good if you like to fish, but if you're trying to build roads and other things, or even farming because the soil has been destroyed, then you're going to not have very good luck or good success. When glaciers enter river valleys, you have a deepening of the valley and creation of these U-shaped forms. Most best known example, I guess, would be Yosemite Valley in California. When the glaciers deepen a river valley and then block the end of the valley with a terminal moraine or deposition of material, you have finger lakes. So here are the Finger Lakes of New York, typical of this kind of surface. If the river flows into the ocean and it becomes deeper, then you have typical fjords, where now the seawater comes in and fills up the river valley of this U-shaped, fills up the bottom of this U-shaped valley that was created by a glacier. And you find them in areas that have been glaciated. This is the northeast coast of North America, but common in Scotland and, of course, Scandinavia and Siberia, many other areas. And then I think I ended with this picture of a fjord in Norway, and this is Pulpit Rock. I've seen other pictures. You've got children out here playing with a Frisbee. And I'm thinking, man, that's just not smart to be up there doing that. But anyway. Okay, I want to mention a few other things related to glaciers before we move on. As I've mentioned to some of you, my daughter lives in Missoula, Montana. And so here's a picture of Missoula. And one of the things to do in Missoula, if you've ever been there, is to hike the M. Have you ever been out there and done that? And so you can see the little trail here going up to the letter M. This is behind the University of Missoula. And I've done that a couple of times, and then it's very discouraging because I'm kind of huffing and puffing going up, and I got passed by children. I got passed one time by a lady who was pushing a stroller with a baby in it. Going up. I said, wow, better get in shape here. So you can hike up. It's a big M up there. But one thing I wanted to point out is if you look all around Missoula, you look at the mountains here, and you see lines on the mountains. See the lines back and forth? Okay. These are all indications of an ancient lake bed, which periodically would drain and then fill up again. It's referred to as Lake Missoula. And so the lines are the level of the lake at particular times. And so you have accumulation then along the lake bed. It's related to an interesting location. This is in the state of Washington. It's called Dry Falls. And it's an area, it's a canyon that at one time, there's a lot of evidence all through this area, that at one time this was full of water and subject to dramatic flowing stream in this region. Well, what happened? Well, during the glacial periods, not just the last one, but previous ones as well, in this part of North America, the continental glacier would come down and would block the flow of naturally flowing rivers within this area. So it would come down in here. Normally this area would drain off to the west. But when the ice would come, it would block and dam up this whole area. And so here is a representation of ancient Lake Missoula. and Missoula would be right there. And so all of this area would fill up with water. Periodically, the ice would break, the lake would fill up so much, or something would happen in the climate, and so the ice dam would break, and all of this water would go flowing off across the state of Washington in a catastrophic flood that would ultimately empty into the Pacific Ocean. And it happened over and over and over again, right there in that area. You can go up and examine it. And so the lake, the evidence of Lake Missoula around the city of Missoula, all of this then is indicative of what's estimated to have been a wall of water 800 feet high when that ice dam would break, that would then flow down, and it would bring debris. There would be glacier evidence. Glaciers would calve off the ice sheet that would have boulders, rocks, and so there's debris across this area. These would be boulders that would be floating on ice, and then at some point the ice would break or melt, and so they'd drop to the bottom, and you have this debris scattered across these areas in this part of northwestern United States. Very interesting area to go and examine and visit, and they tell you all about it out there. So if you're out traveling through that area, take a look at all of this stuff. There are other glacial lakes that existed during these times. One of them is the Bonneville Great Lake. The blue area is the Great Salt Lake, as it's evident today, but at one time it was much larger, included what are the Bonneville Salt Flats. And this would also periodically empty out. And in fact, here's the canyon, Red Rock Pass, north of Lake Bonneville, where the water would release. And you can see the shape of the canyon. Canyon indicates the effect of the erosion caused by this outflow in this area during ancient times. Say ancient, we're talking, 13,000 years ago or thereabouts. Another interesting effect of glaciers happens in Europe. Notice the rivers, the major rivers in Europe. They generally point northwest. So you can look at the Loire, the Seine, the Rhine, the Meuse or the Maas flows through this area, Elbe. All of these rivers, if you look at their shape, they flow off generally in the direction of northwest. Many of these rivers, I'm not sure if all of them, but many of them at one time flowed north, directly north. But what happened was the continental glacial ice came down, invaded this area, and it actually diverted the course of these rivers off to the northwest. Essentially just pushed them west, and so those channels were carved, and they have remained up until today. And so that's generally the cause of this direction in this region. Another thing that happened with continental glaciers in Europe was you had, and it happened in this country, but not to as great an extent. You had areas of ice, and looking at this as a profile now. North to the left, this is where the ice is, and then off to the right, going south, and so the ice would be to the north but not to the south. Remember, during the glacial periods, the ice sheets would advance, they would move to the right, and then they would retreat in the summertime. So winter would get colder, they'd advance, retreat, and if the overall climate was getting cooler, then the advances would be more than the retreats, and so gradually the glacier would march forward, but you'd have this back and forth motion. And one of the consequences is that there was just very little vegetation in this area where the ice was acting within this region. So if you look at the temperature, the ice would be 32 degrees. The areas to the south, especially in the summertime, the bare ground down here would get much warmer. This is rock, this is dirt, and so that would warm up in the summertime much warmer than the ice sheets. So this area would be relatively cold, down here relatively warm, and if you remember our discussion of climate, in these conditions you'd have descending air over the cold area and rising air over the warm area. So you'd have these circulation currents, and many times they would be quite dramatic, quite strong. So strong winds would blow from the north because of this difference in temperature. And it would create dust storms out over these areas to the south. So you'd have large amounts of dust that would blow around caused by these wind currents. And eventually, as you got far enough south, especially as you began to run into some of the mountains in Europe, then this dust would settle out. It would fall down and settle. And this led to the formation of what's referred to as loess. You may have heard of it. And it creates a type of material that's sort of loosely packed. In some cases further down it would become hard rock, but mostly loose packed soil material. This loess, which refers to wind-deposited material, has formed some of the most fertile areas in all of Europe. So if you look around Europe, you know, the many fertile fields, for example, the Paris Basin, a reason for early settlement around Paris was the fertility of the soil within that region. And here you see a map of the distribution. These are the major loess areas in Europe. And all of this area through in Central Europe is accumulated dust-deposited material. Ultimately, most of it traced back to the glacial periods when you have these winds blowing across these areas of northern Europe. It's interesting, if you look at a population map of Europe, you find interesting correlations between these good fertile soil areas. I'll do that. Fertile soil areas and population density. So the darker areas are the areas of greatest population density. Not all of them, of course. So you have the Po Valley in northern Italy, or you have areas in Great Britain, but many of them related then to the accumulation of these loess deposits in Europe. So anyway, just another bit of evidence, consequence of glacial action during the time of the ice ages. Mention something else that has at times been attributed to glacial action, at other times not. There's some evidence that the Black Sea, here's the Black Sea, east of Europe, was much smaller than it is today. The connection between the Black Sea and the Mediterranean is through this area of Turkey. So here you have the Dardanelles, Gallipoli, famous battle site, Bosphorus, the area up around Istanbul. And so this area today is connected. The oceans or the seas are connected to each other. You can get in a boat and travel from the Black Sea into the Mediterranean without any problem, other than, you know, all the traffic here and going through the Bosphorus. But at one time, it was not connected. So the Black Sea was separate. It was like a separate lake. But something happened that ruptured that land bridge that existed. And it's mentioned in the book here, Noah's Flood. Ryan and Pittman talked about this. And the estimate is that 5,000, 6,000, 7,000 years ago, and some put the dates back to the time of the ice ages, something happened to rupture the land connection here. And at that point, water poured into the Black Sea dramatically. So here's generally the shape of the sea before this happened. And they've gone and in some of the areas that at that time were dry land, there's some archaeological evidence of settlements, villages along the shore. And then it all came rushing in. And the point of that book, it's an interesting hypothesis that some of the early legends or tales of flooding to be found, for example, in the tales of Gilgamesh or in the Bible with Noah's flood, may have their origin in what perhaps happened with this flooding of the Black Sea. All of a sudden, the water starts to rise, and probably people without enough time to flee the area lost their life, and so some of that the Great Flood may be associated with this episode, which seems to have truly happened at some time, in the past. Okay, well anyway, let me move on. Okay, so talk about Noah's flood and all of that. So we're talking about degradation and aggradation. Aggradation has to do with the buildup of material. Degradation is wearing it down, reducing the level of the land. How does it happen? Well, volcanoes, of course. One way that you get the accumulation of material. Now, sometimes, if you look at professional literature in geology or geomorphology, they will use the term aggradation. I think I'm getting ahead of myself. They'll use the term aggradation to refer simply to sedimentary deposits, deposits of sedimentation. I'm going to use the term here, and others do this as well, to describe any accumulation of material, any buildup, such as in a volcanic eruption. But a point I wanted to make is that degradation and aggradation happen concurrently. They're always going on at the same time, and so it's not that one happens and then the other starts. No, they're happening concurrently. And what determines whether the landscape is getting higher or worn down is which is occurring more rapidly, what's happening the fastest. Okay, so as I indicated, involves sedimentation, and some will restrict aggradation just to reflect sedimentation. I'm going to use it to mean anything that uplifts the landscape. So you take Mount Everest, tallest mountain in the world. It's located on the border between Nepal and China. It's 29,000 feet above sea level, but you may not realize this, mountain of Chimborazo in Ecuador is further from the Earth's center. Chimborazo is only 20,000 feet. Yeah, Paul?
You're talking about degradation and aggradation. Does this mean that the mass of the planet remains constant?
Mass of the planet remains constant, except for I can't imagine how we would lose mass. We do get every once in a while a meteorite will hit the Earth, and so maybe the mass increases. But no, the stuff that's aggregated and degraded goes somewhere else. It goes to the bottom of the sea, or and so the total amount is the same. Okay, anyway, so why would Chimborazo be further from the Earth's center? It's right on the equator, exactly. And because the equator, there's a bulge at the equator, centrifugal force actually makes the Earth a little bit flattens the Earth at the poles. And so for that reason, anything at the equator is going to be more distant than something that's off the equator. Most of us in here, I'm sure, remember when Hillary and Tenzing reached the summit, article in National Geographic magazine. Over 4,100 people have reached the summit, and there's probably a few more. I did this slide a few months ago. 240 have died trying. Average cost $60,000. The summit of Mount Everest is made up of limestone and metamorphic rocks. Limestone is material that's formed at the bottom of the ocean. Metamorphic rocks are rocks that were formed at one point in time but have been exposed to heating and compression within the earth that have changed their form or their characteristics. And yet they're up here at the top of the mountain. So the top of the mountain at one time, whatever's up there, was at the bottom of the ocean. So it's been deformed and changed, and we'll talk all about this a little bit later. But the point I wanted to make is that Everest is getting higher. Every year it's growing. And so erosion and weathering are taking place. You have snowfall and all of that then comes down and washes down. And yet, the uplift that's whatever it is that's pushing Mount Everest up in the air is happening at a rate that's faster than the accumulation, weathering, and erosion. 20 feet every 100 years, so that's what, 0.2 feet a year? Anyway, growing, yeah.
What is the height of Chimborazo?
It's about 20,000 feet.
So that means that Lord is accounting for 9,000 feet of difference.
Yeah.
Wow.
I think the bulge, I don't remember off the top of my head, several miles. All right, here's some more evidence. Here's a canyon, and there's a river flowing through a canyon. This isn't the Grand Canyon, but notice the shape of the river. Again, looks like a snake. Well, rivers form like this on flat floodplains when they are flowing close to base level. So they're flowing across it just like the lower course of the Mississippi River. You get this back and forth, these meanderings. And yet this isn't a canyon. There's no way this river is going to meander and cut all this canyon. So what happened here? Well, the river is cutting down through the canyon material, but there's something that's happened to raise the level of the land. So the land is coming up as the river is cutting down. So it's like a knife that's continuously slicing into the landscape in the course that developed during a period of time when this was an old age river, when it was flowing close to base level. The water was flowing into the ocean. There was some sea or ocean in the vicinity here. And yet that shape now persists in this canyon, but this is no longer an old age river. It's probably a youthful river because of the uplift of the landscape. And so it's all happening at the same time, concurrently. Brings me to the Grand Canyon. Now, we'll talk more about the Grand Canyon a little bit later, but I thought I'd just mention, sort of in this same context here, what's been happening here in the canyon. The Grand Canyon, began forming, the latest I've seen is about 17 million years ago. At one time, they thought that the canyon actually began forming 3 or 4 million years ago, but I see that the date has been pushed back some latest evidence. And these are sedimentary layers. These are all layers of sandstone, limestone, things that were formed at the bottom of the sea or through some sort of accumulation of sediment. And so that period, what did I say, 17 million years ago, that would put it right about here. This is in the current period, the Cenozoic era. But notice, compared to the age of the Earth, this is just sort of a drop in the bucket, just almost nothing. If you look down at the profile of the Grand Canyon, various sedimentary layers, the Colorado River has been eating down, and it's plowing through Precambrian rocks, and this, all of this, whatever that color, olive green color is, that's what they call Vishnu schist. Schist is a metamorphic rock. Again, a rock that's been formed by compression, heating within the surface of the Earth. Here's what it looks like. This is Vishnu schist down at the bottom of the canyon. This stuff is 1.5 billion years old. They've done radiometric dating of some of this stuff. 1.5 billion, that's about a third, well, let me go to the next. That's about a third of the age of the Earth itself. So the canyon didn't start forming until just a few million years ago. And yet the rocks at the bottom of the canyon are ancient. They are some of the oldest rocks in North America. So how is that possible? A relatively young canyon that has rocks at the bottom that are so ancient, so old. Well, to answer that, The Grand Canyon is part of the Colorado Plateau, which is connected to the Escalante Staircase. And if you've been out there, you know the spectacular scenery and Bryce and Zion and all of that pretty white limestone. That's all part of this Escalante Formation. But the Colorado Plateau is being uplifted. It's just being raised up in the air. And the speculation, and again, we'll talk more about this when we get to plate tectonics, is because there's a fragment of an ancient oceanic plate that's dipping below here. It's just some way down there below all of this, and gradually pushing up these layers of sedimentary rock, pushing them up in the air. And as they go up in the air, the Colorado River, again like a knife, continuously carves the surface and eats into the rock. And so you're down to some of these very ancient rocks that go way, way back in time, at least a third distance back to the origin of the earth itself. And the thing that's interesting about the Colorado Plateau, this kind of thing happens a lot all over the world with the carving and the change and the uplift. But what's sort of unique about this area and what's created such a spectacular canyon is the fact that these layers have remained more or less horizontal. So over these millions of years, they're coming up, but they're staying level, they're staying horizontal. They're not dipping and tilting and fracturing and folding and faulting like so many other areas are. They're just staying more or less uniform horizontal as the river then slices down through them. So that's the reason we have such a spectacular national park in the United States, is because of that particular type of geology. Okay, well let me move on. I'll tell you what, let me go ahead and give you your break now. Remember, we're going to have to leave a little early. So take 5 minutes. All right, let's move on, talk about sedimentation. Remember, we're talking about ways in which land is built up. So rivers, looking at erosion, rivers are transporting, look at all the mud and the stuff being carried by the water. As the river flows along, at some point the water stops moving. In all likelihood, this would be where it enters the sea or a lake. So it comes to rest, and at that point, the particulate matter in the water will settle, will fall out. It's no longer in suspension. And if it flows into the sea, typically you get formations that look like this. Where is that? Egypt. So that's the delta of the Nile River. So these things are called deltas because they look like the letter delta. Now what happens, why do you get this typical shape of these formations? Well, what happens is the water is flowing down and it will seek the lowest level to an outlet to the sea. And so it'll find the lowest level of land. And as it goes, then at some point the water stops flowing and it deposits whatever its load is. So that stuff falls out of the water, and over time in that particular channel, you'll have a buildup of material on the bottom of the stream. And so the bottom of the stream gets higher and higher. As it's raised, then the channel will move. It no longer goes that way because it's seeking a lower level. And so typically you'll get this movement back and forth of the channel as it will fill in this area, that fills up with mud and debris and material, and so then the channel will go somewhere else. And so you get this fanning back and forth as the channel seeks an outlet to the sea and laying down, depositing its silt and its sand, whatever it's transporting, in the process. And so that fanning back and forth across creates these typical delta-like formations. And usually it's very good soil. So alluvium deposited in this manner. So some of the best farming areas in Egypt are in this delta region. not only do you have good soil, but you have the availability of water because of the river to be used for irrigation. Here's another delta that you may not have recognized. This is the Netherlands in northwestern Europe. Several major rivers flow into the sea at this area. So here the Maas or the Meuse, the Rhine flows from central Germany. And all of this then over the centuries has built up these areas in this part of Europe. That's what it looks like today. Not too long ago, though, it looked like this. And of course, what's happened in the Netherlands in this delta environment, they have had a program, a process of diking and draining where they will build blockades across these barrier islands with dikes, and then over the centuries pump out water from behind the dikes into the sea. And so many of these land areas, they're referred to as polder, P-O-L-D-E-R, are actually lower than sea level. So here you see a typical dike, and they'll pump the water out and pump it into these canals. So a lot of times the canals are actually flowing at a level that's higher than the surrounding countryside as they drain this water into the North Sea. And so it's a process that's been going on.
This is a landscape dominated by water, and the Dutch have been holding it back for centuries. But now, instead of just containing the rivers with dikes, they're releasing them into the fields.
Our priority is to protect the towns in the river system by finding space downstream where we can let water into floodplains that will lower the water level in the river, and that means that flooding in towns will not happen.
For the area's rural inhabitants, that's not as unpalatable as it sounds. Noel Hulschmajer's farmhouse used to stand on the new floodplain here, but it's been knocked down and rebuilt on a man-made mound.
We have here a new farm, and we all safe. And now a lot of the water are coming, and we safe, and we going up.
So despite all the memories, your children were born there, but no room for sentimentality?
No, nothing, helemaal niks.
Beyond the dikes, the solutions are even more imaginative.
These homes look incredibly vulnerable, but when the water rises, they do too.
Mike, can you turn it up a little?
They're built on hollow concrete pontoons with flexible pipes for electricity and sewage. And that means they can keep functioning, even when the tide lifts them by as much as 5.5 meters.
In Rotterdam, that technology is being tested to the limit.
And you can see that the building goes up and down every day with the tide.
This pavilion in the old docks, the start of a floating city.
What you're now seeing is that urban expansion is happening in floodplains. They are very vulnerable to flooding. And in that case, a much better option is to urbanize underwater. Because if you do that, the floating area will adapt with a higher water level. So you won't experience any flood damage.
It's expertise the UK is suddenly desperate for. The Netherlands flood czar has taken numerous calls since Sunday and is ready to help.
And I said yes, but you have to make your own solutions. It's a matter of political will. Do you want to solve the problem now and for the future? A matter of money, of course. Do you want to give money to this specific area of politics? We have a fund with €1 billion a year, every year. It's not cut it.
But cuts in the UK are on the horizon, and that makes it difficult to imagine a more innovative future. Rachel Younger, Sky News, the Netherlands.
So flooding, we've had some flooding here in this country lately. One thing that happens over there in Rotterdam, they have some big gates. Rotterdam is Europe's most important port. It's on the Rhine River. Big gates that will close. I forget how much they paid to build those things, to prevent the storm surge, you know, like we've had with some of the hurricanes from going up the river. Now, they don't get hurricanes, but they have some pretty severe storms coming off the North Sea. So they have invested a lot in this flood control. They had a major flood in the Netherlands in 1953, wasn't it? And I think a couple of thousand people were killed at that time. And at that point, they decided, they made, like I said, a political decision to put a lot of money into preventing that from happening in the future. And so, you know, the notion of the little boy with his finger in the dike to keep the flood from coming, well, they don't need that anymore. They've got all these other controls. Okay, well, here's another city where the river's running out into the ocean. Don't know if you're right. You recognize that? That's where my wife was born. Jacksonville, Florida. But notice the St. Johns River flowing into the ocean here, there is no delta. There's no delta there. So some rivers have deltas, but not all of them. The reason for that is because there is a current that flows north. You know, the Gulf Stream flows from south to north, and as material comes out into the ocean, it gets pushed away. And so that's being taken away before there's the opportunity for it to accumulate and form typical delta formation. Here's another river without much of a delta. This is the largest river in the world. This is the Amazon flowing down past some of these cities, Santarém. Here's the island of Marajó. Flows into the Atlantic Ocean. But notice there's not much of a delta up here in this area. Yeah, it changes color. It was brown when I saw it too. But what happens here with the Amazon, the water comes out of the center of South America. There's a current that flows along the coast here. So if you want to find the delta of the Amazon River, all that sediment that's coming out of the center of South America, that's where you have to look. This is the delta area, all of the Guiana areas. This is where you get the accumulation of sediment, alluvium, brought down from the center of South America. Now there's some other areas also without delta. So here's the eastern coast of the United States. This is Chesapeake Bay, and the Susquehanna River feeds it coming down from the north. Here is the Delaware Bay, the Delaware River. There's no delta here. This, if anything, it's just the opposite. So how does that happen? Here's another one. This is South Alabama, Mobile Bay. And so here is the accumulation of material down along the lower course of the Alabama River. The rivers in Alabama come together and form this lower section here. Well, what happens in these circumstances, both here and along the eastern coast of the United States, is you're looking at the effect of changing sea levels. So there's some things going on that are different from just the ordinary accumulation of sediments. Here is a history of the formation of Mobile Bay. You had essentially rivers coming down to the sea, to the Gulf of Mexico. And over time, the advancing of the land and the delta, typical delta formation, barrier islands off the coast. And you have essentially river valley carved ultimately to the sea. But again, with changing sea levels, with the melting of the glacial ice and things that have gone on during this recent couple of 1,000 million years, the sea has moved back. In other words, sea level has come up. So these lower portions of the river valleys now are flooded. And so you have essentially a bay in areas that at one time were all the way down to the coast. And that's true of the areas along the eastern United States as well. You've had changing sea levels that have modified these outlets to the sea from these areas. Well, the most famous delta in this part of the world is the Mississippi River Delta. And the Mississippi, well, let me show you. This is the typical delta formation, the lower course of the river that, of course, drains the center of North America. Now, don't get confused when I refer to delta as this area down here, the southern part of the river, with the area referred to as the Delta in Mississippi. Western Mississippi is referred to as the Delta. It's also an area of alluvial deposits, you know, cotton production and all of that. But that's different. When we talk about the Delta of the Mississippi in this context, we're looking at the lower course down here through Louisiana. And the river comes flowing down. Here's the Red River coming out of the west, flowing down, and all distributary channels maintained by the Corps of Engineers. Now, in this lower area of the Mississippi, the river is naturally depositing sediment. So as the water flows out into the sea, it's depositing all of this sediment, and so it's continuously adding to this delta shape of this delta formation. And so you have all of this land that at one time was mud that was being transported by the Mississippi River and is now accumulated within these areas and eventually building up more and more land. Now, one thing that's happened is that the Mississippi River over the last century or more is being artificially controlled by the Corps of Engineers. So along the river, especially these lower courses, there are a series of dikes that continuously channel the water in the direction of the existing channel. So right now, the natural sequence of events that would normally happen is not occurring. In other words, the river is not being allowed to divert and fill in areas as would happen with a typical delta-like situation or delta-like process. Yeah, Jim?
Is it also true that the channelization of the entire Mississippi Basin by the Corps of Engineers, in some cases Bureau of Reclamation, they channelize areas that previously flooded and diverted that into the Mississippi River as increased flow input? That started back.
That's, yeah. I think that's, I'm sure you're right about that. Of course, land, and this all along the river, there's a good farmland. You know, this is a heavily populated area, and so there's strong pressure to drain and make use of this land, you know, for agriculture, for whatever purpose. One thing that's happened in the Netherlands is that they are moving in the opposite direction. They are taking land away from, quote, civilization or settlement, forcing people to move away from the rivers and then allowing that to go back into swamps so that it will capture some of this flood overflow. Well, here's a schematic of the history of the Mississippi River in this lower delta region. So a long time ago, and I don't actually have the dates on here, but the river flowed down in this direction, south of Morgan City off to the southwest. Well, as this area became filled up with sediment, then the river diverted and began filling in over here. And so they can actually date these areas. This is a sequence then of the water flowing out of the middle of the continent. And so you can see all of them. And today then down here along this the southern distribution area. And so the delta was created in this fashion. But we are attempting to control all of this. Of course, we want to keep the ship channels open. We want to maintain the port of Baton Rouge and New Orleans. And we don't want the river going off where it wants to go. We want to keep it where we want it. And so we're doing all of the diking and draining to try to maintain that. And so here you see some of the diking along the river. Constantly dredging the riverbed, trying to keep it open. Every once in a while, though, nature takes its own course, and so periodically we'll have floods. This is not in lower Louisiana, this is further up the river. But we'll break through one of the dikes, and when it does, vast areas, vast acreages get flooded because much of the surrounding land is actually lower than the river itself. The bed of the river, in some cases, is higher than the surrounding landscape. There's an interesting situation that's been going on now for several decades in this part of the lower course of the Mississippi. You have Corps of Engineers working to maintain the flow of the Mississippi River. There's an area right here where the Red River comes into the Mississippi area, the Mississippi Basin. The Red River comes out of the west, and it flows, and the original flow is just as it's depicted here. It goes down and ultimately exits past Morgan City down what's called the Atchafalaya River in this area. And here you see the Mississippi River to the right. Now they are connected, these two rivers are connected here in two locations. And this has created problems, and it's led to the construction of what's called the old river control structures in this area. And all of this came about because of some poor planning or action without anticipating the consequences. Originally, you had the Red River and the Mississippi flowed parallel to each other in this area. But at some point, the Mississippi, due to the natural bending and meandering of the river, came over and captured the Red River. And so a bend in the Mississippi River intersected with the Red River. And so you had the Red River flowing into the Mississippi and then an outflow further down in this area. And this happened, maybe about 500 years ago, 15th century. When settlement arrived in this area, after we defeated the Indians and started running steamboats up and down the Mississippi River, there was concern because on the Red River, and on several of these rivers, there were massive log jams where all of this debris would just pile up and accumulate. And so one of the things they worked hard to do was to open up traffic on these rivers by removing all of this debris. And the raft of logs on the Red River was something like 160 miles long. There was another one down on the lower Atchafalaya too that was blocking any kind of traffic in that area. Well, people came along and had the bright idea, well, let's get rid of all of these logs and try to promote traffic down the river. Well, this guy, Henry Shreve, he was a steamboat captain in the 1800s, about 1830, 1840, in there sometime. He actually developed he was a steamboat captain. He traveled up and down to New Orleans back from Ohio, and he had all kinds of lawsuits and all because traffic down here was in the hands of a monopoly, and he was breaking the monopoly. But anyway, so he traveled up and down this area, and he actually invented some means for hauling logs out of these log jams, winches and so on. And so he went to work. He decided he would clear these log jams, and he did. And in fact, Shreveport is named for him up in that area. And so now you have more water, you have more traffic. Cleared the one down here on the Atchafalaya. And another thing he did was he cut off Turnbull's Bend on the Mississippi River so you could go straight south. But anyway, as a result of all of this, clearing the logs, changing the course of the river, all of a sudden you discover that the Mississippi River is flowing and water is being diverted. The upper channel gets abandoned, is being diverted into the Atchafalaya. And more water is going from the Mississippi River down the Atchafalaya instead of the normal course of the Mississippi River. Well, that's not good news if you live in New Orleans or Baton Rouge and you have ships and all of that kind of stuff. So the Corps of Engineers comes into the rescue and decided that they will control all of this stuff. So they built some dams. It's referred to as the old river control structure. Go into all the details here. And so that's what's happening now. You have the Corps of Engineers that's controlling the flow of the river, preventing Mississippi water from going down the Atchafalaya. Because essentially what's happening is nature is trying to do what's natural. It's trying to go down the quickest way to the Gulf of Mexico, which is down the Atchafalaya River, not down the existing channel of the Mississippi. And all of this is happening. There was a major, let me see what comes up next. Here's a picture of some of it. And you may wonder, well, why am I so interested in all of this? Well, I read a book by John McPhee, Control of Nature, where he describes, I don't know if you've read that, it's an interesting description of all of this stuff, but it's a very good example of where we are attempting to subvert nature. We're trying to control nature and make nature do something that nature doesn't want to do. In my mind, at some point, humans are going to lose this battle. You know, now it might be 100 years, it might be 1,000 years, but at some point there will be a flood that will be so catastrophic that it's going to come and it's going to wipe out all of this stuff. And lo and behold, the new course of the Mississippi River is going to go directly south. Morgan City will no longer exist, and so it's going to be different. Yes, Jim.
That's what I was going to say. It's a major problem already in Louisiana. In the last 50 years, they've lost 1,500 square miles of land mass. And it's because of what man has done, along with the gas, put the gas lines in there. They have lost that much land mass. This is land mass where you have shrimp, crabs, and everything, you know, breeding and
That's right.
fish and all that kind of stuff. Also, an area which is preventing the storms getting into the New Orleans area, the Pontchartrain area. You do not have that anymore. It's getting worse and worse and worse.
No, that's right. And that's primarily because we've diked up the Mississippi River, and so it's all channelized. That flow that used to fill in all of those swampy areas in southern Louisiana that would naturally replenish the supply of soil in that area is now being diverted straight out into the Gulf of Mexico. And so normal erosion occurs in those areas, and so whatever is there is gradually getting carried out to sea itself. Plus you have the subsidence from removing the, you know, the oil and stuff from under the ground. That's another thing to say. Yeah. That's right. Some of this is for, in particular this northern one, is for flood control. So if there's too much water in the Mississippi, they will divert water down the Atchafalaya. And again, people in Morgan City, which is on the Atchafalaya, are not happy with that. But nevertheless, they've done that and actually flooded areas in southern Louisiana with that fashion. Okay, Mike, let me go just a few more minutes and I'll let class out here. In, let's see, 73, there was a major issue here where it almost got washed away. And they almost lost these dams, and no telling what would have happened, but they dumped 200,000 tons of riprap, that's, you know, rock material, in here and actually filled up a hole that was eating out under the dam, so they saved the day. But I'm pretty sure eventually some of this is going to go. Okay. As sedimentation happens, this material will accumulate. You know, the mud and the silt and the sand, whatever's being transported. When the water stops flowing, then all of that stuff settles out and falls to the bottom of the sea. And of course you have delta formation, but you'll get compaction of the material at the bottom. So as the weight of this stuff accumulates, then the stuff down below gets packed and it gets harder and harder. And ultimately this leads to the formation of sedimentary rocks. So sedimentary rocks come from the deposition of this sediment. So when the wind stops blowing or the river stops flowing, when all of everything calms down, then this stuff will settle out. And so sedimentary rocks are the result of this process. And you can form, and it forms solid rock. Now, This is one type of sedimentary rock. This is called shale. And you can almost see the accumulation of the mud in these layers of shale as it's being deposited. You'll have the laminar character to it, and again, the layering indicates the age at which various sedimentation events occurred. So shale is a sedimentary rock. Sandstone is a sedimentary rock. Again, if the material that's being moved is sand, sand is coarser grained material than silt or just ordinary mud. Sometimes in a desert area, so you can look at the layering and tell whether these were dunes at one time, or was this laid down horizontally at the bottom of a lake. And so sandstone is a type of sedimentary rock. And of course, we've talked about limestone. Limestone is formed from the accumulation of marine organisms primarily. And in some cases in the sedimentary rocks, such as this coquina rock, you can see actual evidence of the shale, the fossilized evidence of the marine organisms that created this lime rock. Usually in limestone, though, you don't see it directly because it's microscopic. So again, this white limestone, white rock. Cliffs of Dover, this is a very fine kind of limestone, this essentially chalky material. And it's formed from this stuff. It's coccoliths about 20 million years ago. Microscopic in nature, so you can't actually see them very well. So one of the consequences of sedimentation is the formation of sedimentary rocks, which then, in fact, most of the Earth's surface is covered with sedimentary rocks. And you get the karst formations that we were talking about. Why are sedimentary rocks important? Well, for two reasons. 75% of the Earth's surface is covered with sedimentary rocks. So 3/4 of the Earth's surface. And then secondly, they provide a record that we can use to analyze the history of these rocks. So we can look down and examine the fossil remains of these organisms that then make up some of these sedimentary deposits. So let me ask you a question. We've talked about weathering, erosion, sedimentation. If that were all that were going on, the planet Earth would look like a billiard ball. In other words, completely smooth. I started to say flat, but it's not flat. Or a bowling ball, let's say, without the hole in it. You know, because the high elevations, the mountains would be worn down by the action of the weather. The low areas are filled in by sediment, so the ocean beds would be filled in. And so eventually, with the passage of time, the Earth would look completely smooth, if this were all that were going on. But the rest of the story, of course, is that it is not all that's going on. What causes relief? Now, we have to leave early, so I'm going to let you think about that until next week. And so we'll pick up with all of this and talk about what brings relief. Thank you.